morning. I think we will continue with chemical propellants in this class, namely the criterion for choice of propellants, which are essentially chemicals with which we are considering, right. What did we learn so far? We told ourselves all the propellants, all the chemicals which are used as rocket propellants must have low atomic mass, such that we have low molecular mass of products, point 1. Point 2, we also told ourselves maybe it must be dissociated. What do you mean when I say that the products of combustion must be dissociated? Instead of having water, if I could have something like H atom or O atom or OH atom, well, the specific heat will be smaller and therefore the temperature will be larger. Maybe I will take a look at it subsequently, maybe in the next class. Third, we told ourselves from gamma point of view, it may be better to have more complex products of combustion. This complex products is against what we decided here. And towards the end of last class, we also defined when the heat release from combustion, heat release from chemical reactions of these propellants, and we defined a term heat of formation. What did we say heat of formation is? We told ourselves heat of formation relates to a substance with which we are interested, maybe the heat required to form the substance at the standard condition being 1 atmosphere pressure and say 25 degrees centigrade, this is the standard condition. The heat required to form the chemical or the substance at the standard condition from the elements which constitute the substance, again at the standard condition, we defined as heat of formation. This is the way we use it for products, for chemicals, anything what we require. Therefore, what is the heat which is released in a chemical reaction? We told ourselves, I will write it in a little different way. If I have products and the sum of the products, the heat of formation of the products, let us say products consist of Ni, N1 moles of one, N2 moles of the second substance and so on, and each of these substances have a heat of formation, standard heat of formation, which is given by delta F corresponding to ith substance. I have heat of formation of the ith substance. Well, this defines the heat of formation of the products. Now, I subtract from it the summation of heat of formation of the reactants. Again I say ith substance, heat of formation at the standard condition for the reactants, and then if there is a decrease in the heat of formation, I say some energy is released in the combustion. Let us be clear about this notation. What am I telling here? I have in the reactants, I have, let us say, the chemical 1 having 1 mole, maybe N2 moles of chemical 2 forming, let us say, N1 moles of product 1 plus N2 moles of product 2 and so on. All what I say is NiCi, 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 I going from 1 to 2 for the reactants, I going from 1 to N for the products, and this is how we are saying is the heat of combustion. And what do we want? We want this heat, or which we also called as Q, to be as large as possible. And for this we looked at heat of formation of certain substances. We looked at heat of formation of, let us say, methane, ethane and so on, propane, butane and all that, up to kerosene, which we called as dodecane, C12H26, and we found that the heat of formation keeps increasing in the negative direction for this series of hydrocarbons. Therefore, we told ourselves if the substance or the chemical is little more complex, maybe the heat of formation is higher. And this we also saw in the example when we saw CO2 and when we saw CO, we found that the heat of formation of CO2 was something like almost 386 or 387 kilojoules per mole, whereas CO we found it was 110.5. In fact, we used the reaction to find out the heat of formation of CO, heat of formation of CO2, little more complex means the heat of formation is higher. Mind you, it was negative 387 minus 105.5 kilojoule per mole, right. Therefore, we would like to know for a chemical to produce maximum heat release, what should be the choice of heat of formation of the substance. That is what I am trying to get at, and this is the only thing which is left. Once we do that, maybe we will be a little bit wiser in the choice of propellants to be used for as rocket propellants, and that is what I am trying to do. Let me get back to the slides here. What I have shown here is for fuel, say methane minus 75, ethane minus 85, propane minus 104, butane. See, it keeps on increasing until we come to kerosene. It has increased and it is a negative quantity, that means increasingly negative quantities. If I have a polymer, what is a polymer? Polymer is a slightly different animal in the sense we are looking at something like a chain which consists of maybe CX, HX, O, CX, HY, OZ, and it keeps on as chains, maybe M times. It keeps on prolificating like this. We find that the heat of formation of some of these polymers, and we will look at polymers in some detail like polybutadiene and all that when we deal with solid propellants. These have a heat of formation as shown in this slide as something like minus 80 kilojoule per mole. When we talk of other fuel like hydrogen, well, hydrogen at the standard condition is an element and therefore the heat of formation is 0. I think for different fuels we therefore say, well, for hydrocarbon fuels it keeps increasing as the complexity of the substance increases. For a polymer it is around, let us say, minus 80 kilojoule per mole. For hydrogen, which is an element, and again at the standard condition it is 0 kilojoule per mole. Is it clear? Now I want to also define some more substances. In the last class we told there are certain substances which are known as explosives. We keep on reading about explosions here and there. What is the difference between an explosive and a fuel? When we have fuel and oxidizer already mixed together, premixed very well, or if not premixed, it is a form of a molecule itself. That means fuel and oxidizer are an integral part, either extremely well mixed or else it is a part of the substance itself. Let us take one or two such explosives and that will be very instructive. In the last class I started with nitroglycerine. When we say nitroglycerine, it is basically we are talking of glycerine, and glycerine is derived from propane, and in propane what you do is you take C3H8 which is propane, you take 3 of the 8 H atoms, substitute it by OH, that means we have C3H5OH3. This becomes something like 3 of OH. This is known as propane triol. That means it is just an alcohol of propane. Now in this you take the OH out, you substitute OH, instead of OH you put something like a nitro radical, you put C3H5ONO2 3 times, and this becomes nitro based on glycerine which is propane triol, and this is known as nitroglycerine. And this has a heat of formation as shown here, maybe in the next one, you see that the heat of formation of nitroglycerine is around minus 370. And how do you get it? You do an experiment, you find out you have minus 370 kilojoule per mole. But why did I take this particular expression of nitroglycerine here? I want to know whether nitroglycerine can act as an explosive. It has oxygen, it has fuel, it can burn together to give me, let us say, CO2 plus H2O plus maybe CO, maybe any of the things it could form. But if I look at the substances which are there in nitroglycerine, I find it has 3 of carbon. If we take hydrogen, it has 5 of carbon, 5 atoms of carbon, 3 atoms of, I am sorry, 5 atoms of hydrogen, 3 atoms of carbon, and if I take O here, it has 3 3, O has 9. That means it has 9 atoms of oxygen, 5 of hydrogen, 3 of carbon. Now if I want to oxidize the carbon, I need something like 6 atoms of oxygen to form CO2. If I want something like 2.5 atoms of oxygen to form CO2, 2.5 atoms of oxygen to form, or 2.5, why even less, right? I have 5 atoms of hydrogen, therefore I have 2.5 of O is all what I require, 6 of O to form, let us say, carbon dioxide. I think I should repeat this again. I think this part will be clear. In nitroglycerine molecule, I have 3 atoms of carbon, 5 atoms of hydrogen and 9 atoms of oxygen. If I want all the carbon atoms to form carbon dioxide, well, I need something like 6O. If I want to oxidize all the 5 atoms of hydrogen to form water, well, I need 2.5 O. And therefore, all what I require for complete oxidization is 8.5 O. But I have 9 O. Therefore, nitroglycerine could still act as an oxidizer. Even though it is an explosive, it has still balance oxygen left, which can still be used for oxidizing, and nitroglycerine, we say, is an oxidizing agent. I think I should repeat it because it is something which is important. Let us take a substance like HNO3, nitric acid. If I take nitric acid, I have 1 atom of hydrogen which requires half atom of oxygen, therefore I am still left with 2.5 atoms of oxygen, therefore nitric acid can be used as an oxidizer. That means it can still be used as an oxidizer even though it is an acid. If I have a substance like ammonium perchlorate, which all of you would have heard of it, it is a very widely used oxidizer for solid propellant rockets. The formula is ammonium NH4 ClO4. You find, well, I have 4 atoms of oxygen, but I have 4 atoms of hydrogen requiring only 2 atoms of oxygen for oxidization. I have chlorine, which is again an oxidizer, therefore it can also be used as an oxidizer. Similarly, if I have nitroglycerine, nitroglycerine can react by itself. I can use it as a propellant directly, but I can also use it as an oxidizer in combination with some other fuel, and still I can use it as an oxidizer, or else I can also use it in isolation as nitroglycerine itself. Similarly, if I take something like H2O2, which is hydrogen peroxide, I do not need all the O to form water, I am left with 1 O, and therefore H2O2 can also act as an oxidizer. Mind you, H2O2 is an explosive, nitroglycerine is an explosive, all these are all substances, but some of them, even though they are substances in which fuel is there, it can still act as an oxidizer. And therefore, let's take one example of a fuel. I started with nitroglycerine, which was an oxidizer. Let's take an example of a fuel which is an explosive which can act as a fuel. The simplest one is maybe this wood, which is cellulose. What I take is, if I take the formula for cellulose, cellulose has a molecular formula C6H10O5, and it consists of this in several places, like n times it gets repeated, like we will have C6H10O5, again C6H10O5, and so on n number of times, and this is how cellulose or paper is made of. Now we can also write this above formula as, I can write it as C6H5 into OH5, and therefore I say yes, it consists of a number of these molecules together, maybe n of them together. Well, this is the equation to cellulose or formula to cellulose, and suppose I want to nitrate it, that means I want to make nitrocellulose. I take some of the OH over here, substitute it by ONO2, and what I get is maybe part of them, not all 5 in the molecule. I get C6H5ONO2. I take X of the 5 over here, and the balance OH is still available as 5 minus X, and this is to the power to n number of times this gets repeated. Now what is it we have done? We now have the formula for nitrocellulose, which is now C6H5, the nitrate ONO2 X times, and OH 5 minus X times. Now if you look at this, C6 carbon, 6 of them requires O2, that means I need 6 of oxygen, that means 12 of oxygen atoms. H2O, this requires 5 by 2 of oxygen atoms, because H2O is what is formed, and then again I have H over here which requires more oxygen, but the oxygen which is available is only 1 plus 2, 3 X times, and here O 5 minus X is already available. Therefore, the availability of oxygen in nitrocellulose is much lower than the amount of carbon and hydrogen which is there. Therefore, in essence, the oxygen available within the molecule is much less than the fuel component of carbon and hydrogen, and therefore nitrocellulose we say is fuel rich. It can dissociate by itself using the small amount of oxygen, but it cannot form completely oxidized species, since carbon and hydrogen are more than the oxygen available, and therefore it is also used as a fuel. I use it as a fuel because the component of fuel in the nitrocellulose is much greater than the amount of oxidizer in it. And this nitrocellulose, if you were to go back and look at what is the heat of formation, it has a large negative value which is minus 670. We talked of N2H4 the other day, hydrazine, which is again an explosive, which is plus 50.3. Therefore, you have all these substances, maybe including an explosive, which could act as a fuel, and these are the heat of formation of the different fuels. Therefore, you see the heat of formation of fuels varies from something like a positive number of plus 50 to a large negative value of minus 670, and it would still keep varying. Now we go back and take a look at what is the heat of formation of the oxidizers. Well, an oxidizer, now I can go a little faster. Oxidizer could be oxygen. Oxygen is an element. At standard condition the heat of formation is 0. If I have nitric acid, well, it is an oxidizer, it's minus 171. If I remove H from it and if I make into something like dinitrogen tetroxide, N2O4, which is again a volatile liquid, I get something like plus 9.63 kilojoule per mole. I talk in terms of other oxidizers, solid, ammonium perchlorate, which I just now said, NH4 ClO4, NH4ClO4 over here. It has a heat of formation of something like minus 295. If instead of the perchlorate radical I use the nitrate radical NH4NO3, I have the heat of formation minus 365. Therefore, you see the heat of formation also widely varies, and for certain explosives like nitroglycerin it is minus 370, for hydrogen peroxide it is minus 187. Therefore, I try to put all these things together just to get a feel for the problem. Well, nitroglycerin has a large negative value, N2O4 has a slight positive value, and this is the variation of this between minus 370 to something like 9. This is for oxidizers, and similarly for other substances, which are the products. What are the products we have been handling? We have been telling, well, carbon gets oxidized to CO2 or CO, maybe the hydrogen gets oxidized to H2O. Therefore, the products are essentially CO2, maybe CO, maybe H2O, and so on. If I have aluminum in the metal, I could form aluminum oxide, and these are some of the products which we are interested. And if you look at the heat of formation of some of these things, which we worked out in class again, it was something like CO2 has minus 397 kilojoule per mole, CO has minus 110, water has minus 296. Mind you, this is important. When I say water, why is it water? Because I am looking at the standard condition of 25 degrees centigrade, and at that pressure is not that important for a liquid, right. Therefore, under standard condition it is water, therefore water has minus 296. H dissociated, we found it is plus 217, OH dissociated is again a high value 395, but if I take aluminum oxide it is extremely large negative value minus 1670 kilojoule per mole. Well, these are some heat of formation which is given to you, and how do you get it? They do experiments, give the heat of formation. Now why is it we are interested in? We would like to have propellants or rocket propellants or chemical propellants, rocket chemical propellants, which will give as much Q as possible. And to be able to get high value of Q, we just now told ourselves, well, the products net heat of formation minus net heat of formation of the reactants minus is what gives me the value of Q. Therefore, what is it I see from this? If the products could have individually negative values, and if the products could have high negative values, then this negative become positive, I could have high value of Q. Therefore, one of the requirements of chemicals which can be used as propellants is they must have large negative values of heat of formation. Mind you, what do I say products? By products I am not talking of chemicals, I am talking of maybe P1, P2, P3, or rather I am looking at CO2, H2O, CO. What are the products formed? The products must have, I should write this as products having large negative values of heat of formation. Is it okay? Similarly, if I talk in terms of the reactants, which are essentially the propellants, what should they have? Minus and minus becomes plus. Therefore, if the reactants would have positive value of heat of formation, it is better for me because I have a more positive number. Therefore, based on these logics, all what we say is, if I have something like propellants, let us put it down again. If I have a single chemical or a single substance going propellant, maybe or a combination of propellants, giving me something like products, the products should have large negative values, whereas the propellants must have small negative, or better to have large positive value. Why did I write small negative values? Because if the heat of formation is positive, the substance is basically unstable. Why is it unstable? Because you are supplying so much heat to form the substance that it cannot remain so in the standard condition, and therefore the general thing is, why should it not have a small negative value instead of a large positive value, which is not possible. In general, some of the substances like N2O4 have small positive value. Some of the explosives have positive value, we will consider these explosives earlier, but in general most of the substances like kerosene or other substances have negative values. But the desirable feature is a propellant should have large positive value, because large positive value makes the substance unstable. We sort of compromise and tell ourselves, well, a small positive value or a small negative value is all that a propellant should have. This tells us what is the choice from the heat of formation point of view, and this is all what we require to know about choice of chemical propellants. Therefore, if this part is clear, maybe subsequent things are quite simple. Therefore, we tell ourselves the choice of propellants for rockets basically should have propellants which have positive value of heat of formation or small negative values, and the products they form should have large negative values. I think this part must be clear, and we will do one or two problems towards the end of this class, it will become further clear. But question is, If I have, let us say, propellant, like let us say I consider a propellant like butane, but unfortunately butane is a gas and it is difficult to use, but let us take this example, plus I have oxygen as the oxidizer. Butane has the formula C4H10 plus oxygen. Let us say it completely burns into carbon dioxide, therefore I get 4CO2, plus I have H2O, 5H2O, therefore I get 5. Now I want to balance this reaction, therefore I find 4, 8, therefore I have 8 of oxygen plus 5, 13, therefore I get 13 by 2 of oxygen. So I can write this reaction as C4 multiplied by 2, 2 C4 H10 plus 13 O2 gives me 8 CO2 plus 10 H2O. What is this reaction? In this reaction we form completely oxidized products of combustion. I cannot oxidize water more than water. I cannot oxidize carbon dioxide further than this. Therefore, these are all completely oxidized products, completely oxidized. And when we form a reaction in which the products are completely oxidized, we call the reaction to be stoichiometric. Okay. You know, what do you mean by stoichiometric reaction? The proportion, stoichio means element, metric means proportion in Greek, and therefore we are talking proportion of the fuel and oxidizer such that we form completely oxidized products of combustion. This is what we mean by a stoichiometric reaction. But the question is, if I have butane as a fuel, as a rocket propellant, oxygen as an oxidizer, what is this? Is it possible that the variation of stoichiometry, instead of having something like 13 of oxygen, 13 moles of oxygen for every 2 moles of butane, will something like 15 moles of oxygen give me better value of C star or better value of temperature or better value of heat release? Will that be better? In other words, I would like to consider proportion of fuel and oxidizer what I require. When we studied the subject of combustion, we talked in terms of equivalence ratio, fuel air ratio, and we said equivalence ratio is fuel air divided by fuel air under stoichiometry. But in rocket tech parlance, or the terminology used in rockets, we use the word mixture ratio, and mixture ratio is defined as mass of oxygen or mass of oxidizer divided by mass of fuel in a chemical reaction. Let us illustrate it. I deliberately took this example. If I want to find out what is the mixture ratio of this stoichiometric reaction, what is the mixture ratio? Let us put it down. Can we do it? Mixture ratio for stoichiometric combustion of butane with oxygen is equal to mass of oxygen is 13 into 32, the amount of fuel is 2 into 12 fours are 48 plus 10, which is equal to 13 into 32 divided by 2 into 58. Is it all right? That is, the mixture ratio for this reaction is something like 3.6. Therefore, if I use a fuel in the proportion oxygen to fuel in the proportion 3 to 2.6, I get completely oxidized products of combustion. Now I take another example, and how do you calculate the heat release? All what we do is the heat release for this reaction is equal to 8 into minus the value of CO2 was something like 386. How much was it? Heat of formation. Let us go back, it is in front of us, 397 plus I have 10 into water, water is minus 286 minus the heat of oxygen is 0 as an element, butane is slightly lower, I think it is minus 105, minus 124.7, that is 2 into minus 124.7 is the heat liberated in this reaction. For 2 moles I am getting this amount of heat, and therefore this becomes the decrease I have to look at. This is the heat of formation of the products, heat of formation of the reactants. I am going to say how much this has decreased, therefore this is minus, therefore I get 8 into 397 plus 2860 minus 2 into 124.7, so much kilojoules of energy which is liberated. And this is how we calculate the heat liberated in this stoichiometric reaction. Suppose instead of having stoichiometric composition, I take, let us say, I put extra oxygen into it, like I say I take oxygen amount as 15 instead of 13. C4 H10 plus I have 15 O2 giving me, again what is this reaction going to give me? I have excess oxygen, therefore I still get 8 CO2 plus I get 10 H2O plus I am left with 2 of oxygen. Is it all right? Because I have more oxygen than available. The oxygen first oxidizes the carbon and the hydrogen to form carbon dioxide and water, and this is what I get. What is the mixture ratio for this reaction? Is equal to, I get 15 into 32 mass of oxidizer, mass of fuel 2 into 58, we just now said it is 48 plus 10, 58, and this gives me a value of as something like 4.14. And how do I get? That means the mixture ratio has gone up from 3.6 to a value of 4.14. And what is the heat release in this reaction? Is it going to be any different from that one? It will be same, because oxygen here has nothing, therefore the heat of reaction is still at the same value over here. Now let me consider the third one, in which case I have less of oxygen available. I take the same reaction, 2 C4 H10 plus, now I say instead of giving 13 for stoichiometry I give 11 of oxygen. That means I am starved for oxygen. If I am starved for oxygen, what is going to happen? I cannot get all CO2, I cannot get 8 CO2, I cannot get 10 H2O. The reason being, if this is there I need 16 plus 20, that means 26, whereas I have only 22. Therefore this is not possible, or this is not possible. Somewhere I have to balance it. One of the ways which we could do is to be able to find out, that means I cannot get all carbon dioxide, I cannot get all water, maybe I am going to form something like CO, I am going to form OH and other substances, because there is inadequate oxygen to form carbon dioxide and water. Now how do I determine this? I cannot just like this determine, I have to do an analysis for the equilibrium composition of the products at a given pressure and temperature, which means I have to use chemical thermodynamics to be able to determine this composition, and that I will do in the next class. But before I do that, instead of doing the detailed dissociation and chemical equilibrium or equilibrium of the products is what we have to consider, there is a slightly easy method of doing this problem. What is it we do? We say hydrogen is very reactive, and therefore all the 10 atoms of hydrogen, they search for oxygen and get converted into something like 5H2O, that is 10 pick up the 5 oxygen from here. I had originally 22 oxygen, I have removed 5 from here, therefore I am left with 17 oxygen. And now out of the 17 oxygen, what is going to happen to me? Yeah, you have 20 atoms, therefore I have 10 H2O, therefore I have 10 over here, then I have 12 left. Was this your point? Okay, that means I have 20 atoms of hydrogen requiring forming 10 H2O as it is here, because hydrogen is very reactive. I am left therefore with 12 atoms, but here I find I have 8 of carbon, therefore I am left with 8 of carbon, and I cannot form 8 of CO2 because this will require 16 atoms of oxygen, whereas I have only 12. Therefore what I do is I say, well, I have 8 of carbon, let me first use the 8 of O to form 8 CO, and if I still form 8 of CO, I am left with, again out of 12, 4 of oxygen, and what I do is I use these 4 of oxygen to take 8 of CO, form out of the 8 I remove 4 and I form 4 of CO2, and therefore the reaction will now look like 2 C4 H10 plus 11 O2 gives me first hydrogen, that means 10 H2O, plus I get 4 CO2 plus 4 CO. Let me repeat it. You know, some of you have done it in your explosion course, but all what we are telling is when there is insufficient oxygen, first the oxygen attacks the hydrogen because hydrogen is very reactive, or rather the hydrogen removes the oxygen and all the hydrogen gets oxidized to form water. The balance of oxygen oxidizes the carbon to form carbon monoxide, and still if some oxygen is left, the balance or the part of the carbon monoxide is converted to CO. I think you all should practice this, and therefore you have a reaction wherein now you get this one. What is the heat, what is the mixture ratio of this particular reaction? Mixture ratio of this reaction is equal to 11 into 32 divided by 2 into the value of 58, and this gives a number as equal to something like 3.03. And what is the heat liberated in this reaction? The heat liberated in this reaction is minus of 10 into the heat of formation of H2O, plus you have 4 into, this is a minus value, plus 4 into this, and minus of the total thing minus the heat coming over here. And is it going to be higher or lower compared to stoichiometry? It will be lower because CO has a value which is minus 110, CO2 has a higher value minus 297, and therefore you find that when a reaction is somewhat fuel rich, when a chemical reaction is fuel rich, that means it is short of oxygen, the value of Q comes down. Whereas if it is oxygen rich, then Q of combustion, Q is same as stoichiometry. And this is the maximum heat which is possible in a chemical reaction, right? If this is so, I again ask myself the last question, oxygen rich means the mixture ratio is greater than mixture ratio stoichiometry, fuel rich means mixture ratio less than mixture ratio stoichiometry. Is it right? Now I want to plot these results out. Let us plot it out. We now see, our aim is to get a high value of temperature, or we are still debating what must be the choice of the proportion of fuel and oxidizer to be used as rocket propellant. So now I want to plot this out. I say what is the heat release in a reaction. Suppose this is stoichiometry, I plot it as a function of mixture ratio, and this value I call as mixture ratio stoichiometry. I find anything more than this gives me the maximum value of heat release, whereas below this I keep on dropping because unoxidized or not completely oxidized products of combustion are being formed. Is it all right? Now I want to convert it into temperature. How will I convert it to temperature? I tell myself, well, this is the fuel rich part, this is the oxidizer rich part. Right? I want to convert it to temperature. How do I convert it? We calculated in fact the heat of combustion or the heat which is liberated in the chemical reaction by looking at the products, heat of formation of the products. We said it must be less than the heat of formation of the reactants, and that is the deficit is the heat which is generated. Therefore, if I were to divide it by the summation of the molar specific heats, this will give me something like the temperature minus the initial, it will give me the combustion temperature. That means specific heat into the number of moles into the temperature increase is the heat release. Therefore, Tc is equal to Q by Cp, and now again I take the same thing, mixture ratio stoichiometric, and this is mixture ratio scale. Now this is the temperature scale. You know, how should the graph look like? Well, we still need to do something. Here I have moles which are coming in. I need to be able to convert it, because I will say per mole. Here the number of moles are varying, because in one case I have different number of moles, in the other case I have different number of moles. A direct comparison from this to this might be a little difficult, right? Therefore, what we could probably do is convert the heat release into heat release per mole. Let's do that exercise. If you were to do that exercise and plot on a graph, maybe I'll go to the left side. Q per unit mole, or which is similar, Q per unit mass as a function of mixture ratio, and then I again put mixture ratio stoichiometry. How will that curve which was like this translate over here? Let's do this exercise. Let's again go back into these equations and see. For stoichiometry, you have C4H10 plus 13O2, 2 of this. When it was fuel rich, the number of moles increased, and therefore even though Q is same, as I become more and more oxidizer rich, what's going to happen? We plotted the heat release Q, so much kilojoules, as a function of equivalence ratio or mixture ratio, and the mixture ratio, you said this corresponds to mixture ratio stoichiometric. This corresponds to the oxidizer rich, because mixture ratio is defined as mass of oxidizer divided mass of fuel. This is oxidizer rich zone, and this is the fuel rich zone. What is it we found? When the oxygen content was more than what is required for stoichiometric, the heat content does not change, in fact it remains same, whereas in the fuel rich side, since we are not able to burn all the carbon and hydrogen atoms, the heat release keeps coming down. Therefore, we had got a plot of Q versus mixture ratio. Here it is mixture ratio, this is mixture ratio stoichiometric, and we had got a plot of heat generated versus mixture ratio to go up to the stoichiometric mixture ratio and thereafter remain constant. But let's take a look at this figure again. Supposing I want to plot, instead of plotting Q on this axis, supposing I want to plot Q divided by the number of moles of products which are formed, then what is the type of behavior what I get? See, ultimately I am interested in finding out the temperature. Therefore, I want to find out for per unit mass or per unit mole, if I can divide by specific heat, I get the temperature. And therefore, let us first find out what is the value of heat release per unit mole in the product. Now, again I plot over here, this my axis is mixture ratio, this is mixture ratio stoichiometric. Now, what is happening? As the oxidizer quantity increases, I am left within the products with more and more of oxygen, that is the number of moles in the product increases, and therefore if this is the value of heat release per mole corresponding to this point, the curve begins to drop because the number of moles are increasing in the product. How about in this case? Since it is fuel rich, I am not able to form that much of moles now, and therefore the number of moles decrease, and therefore this curve would become a little shallower here. Rather, the peak value of heat release per unit mole is still at stoichiometry, and either side, in the fuel rich side and in the oxidizer rich side, the curve begins to droop. In other words, the amount of heat release per unit mole has a behavior which gives maximum at the stoichiometric mixture ratio and falls on either side of it. Now, instead of expressing heat release per unit mole, I can also have a similar figure. That means now I say heat release per unit mass of products, that means Q, so much kilojoules per kilogram of product, divided by as a function of mixture ratio. Well, it will be exactly similar, and I get a curve something like this. This corresponds to the stoichiometric mixture ratio. Going one step further, I divide this Q per unit kg, something like kilojoules per kilogram, by the specific heat, and therefore now I can get the value of temperature versus mixture ratio, and this is what I show in the next figure. Namely, I get a plot wherein the plot is like this. We must be able to differentiate between the total heat release and the heat release per unit mass, and this heat release per unit mass when divided by specific heat will give me the value of the temperature, which has a behavior something like this, which I subsequently discuss. But there is a subtle difference. When I look at specific heats of substances which are formed in slightly fuel rich conditions, under fuel rich conditions you are forming substances which are little weaker, CO instead of CO2, and we found that diatomic species have higher value than monatomic species, triatomic species have still different values. That means as the atomic number or the diatomic becomes triatomic, the specific heat increased, and therefore we find that specific heat is slightly lower in this region compared to the stoichiometry, and therefore if I plot mixture ratio stoichiometry, here this is mixture ratio stoichiometry, we are plotting mixture ratio here, I am plotting Tc over here. Instead of maximum temperature happening, it will occur at the fuel rich condition, and I will get some shape like this. Why did I say this? You find that when a substance is fuel rich, I form more of the smaller elements, CO instead of CO2, and therefore CO has less specific heat compared to CO2, and since I am dividing by the value of specific heat, my peak changes from stoichiometry to this. Even though Q per this remains the same, the specific heats are lower as I go along this direction, and therefore the peak changes by this particular one. It is not very noticeable, but still we must remember this. The peak temperature occurs not at stoichiometry, but at slightly fuel rich condition. This is your, and this was your oxidizer rich, right? Is it all right? I think let us remember this. Slightly to the left, that means peak temperature occurs over here. Let us put the last point across. What is going to happen to the molecular mass of the reactants? Or molecular mass of the products? If mixture ratio is equal to stoichiometry, what is it we got? We got 8 CO2 plus 10 H2O, therefore the molecular mass is equal to 8 into 44 plus 10 into 18 divided by 18. If it was more than stoichiometry, that is mixture ratio greater than stoichiometry. When we had something like instead of 13 I had 15, what did I get? I got 8 into 44 plus 10 into water 18 plus 2 into 32 divided by 8 plus 18 plus 2 20, right. I am looking at the mean molecular mass of the products. If I had something like mixture ratio which was less than mixture ratio stoichiometric, what is it I get? I still got water 10 into 18, and then I found I had 4 of 32, 4 of 44 carbon dioxide plus 4 of CO, which was CO is 12 plus 16 28 divided by 4 plus 4 plus 10 18. What I am looking at, the mean molecular mass of the products for stoichiometry for something mixture ratio greater than stoichiometric, that means this is oxygen rich. I am looking at mixture ratio less than stoichiometry, which is fuel rich. And what are the values? Let's put down the values. I thought I had calculated, I am not very sure if I brought it. Yeah, it should be here. Maybe this must be something like 29.5. (1102) is 26. Let's make an assessment rather than have the numbers clearly. What we find is, for stoichiometric I have this, when the mixture ratio is greater than stoichiometric, I am adding higher molecular mass, therefore the molecular mass is higher. If I have mixture ratio less than stoichiometric, I am adding substances which have lower value of molecular mass, and rather I can plot this as the mixture ratio increases, of the products, mixture ratio, this is stoichiometry, I get as the mixture ratio, the molecular mass increases. And what is it we were ultimately interested? We were interested in the value of under root Tc by the molecular mass, because C star went as RTC, RTC is R naught divided by molecular weight into Tc, and of course gamma I am not considering. If I were to consider Tc by m versus mixture ratio, I find if I have stoichiometry, mixture ratio stoichiometry, my temperature peaked slightly in the fuel rich region, my molecular mass is increasing over here, and therefore the value of this will peak in the fuel rich region. That means in my fuel rich region I will have a higher value of C star compared to stoichiometry and in the oxygen rich region. Let me replot this figure because this is something which is important. The value of C star as of plotted as a function of mixture ratio, and this is mixture ratio stoichiometric, this is we are considering fuel rich, oxidizer rich, will be maximum in the fuel rich side. Why it is higher in the fuel rich side? Because the molecular mass is smaller in the fuel rich side. We also find that the maximum temperature also occurs little bit on the fuel side, and therefore the net effect is I have higher performance in the fuel rich, and therefore one of the criterion for choice of propellants is the propellant must be fuel rich. All propellants used are fuel rich propellants. In other words, if I have stoichiometric reaction H2 plus half O2 giving me H2O, what is it I am telling? The mixture ratio in this case is going to be half into 32 divided by 2, that means we are talking of mixture ratio of 8, which is stoichiometric, but in practice what we use is mixture ratio between 5 and 6. The reason being, yes, I get advantages of the lower molecular mass of the products, and also to some extent the saving from the specific heat. Therefore, what we have done in this class is we have told ourselves for the choice of propellants it is better to have fuel rich propellants, that means mixture ratio less than mixture ratio stoichiometry. I will just go through the transparencies on this or the slides on this before I stop this class. Maybe in the next class we will take a look. As you see, the temperature is more slightly in the fuel rich side than in the oxidizer rich side, and you also see therefore C star is higher in the fuel rich side compared to the oxidizer rich side. In the next class we will take a small example, and also we will try to take a look at what are the effects of dissociation, how to calculate with using equilibrium or chemical equilibrium, and that is what we will do. Thank you then.